I've decided to change the order in which I cover some topics and to jump forward to Chapter 7 and cover some information about linear transformations, which I think is useful to see before we do some of the intervening material. I'll have a little bit more to say about why I'm doing this in class, but I'm not actually changing the topics which we're covering, I'm just changing their order. So, a very basic definition in the subject is the following. Suppose we have two vector spaces V and W. A linear transformation from V to W okay, that's what I'm defining, is a function f mapping V to W, satisfying some conditions. So it's a function from V to W, but it's not just any function from V to W. The requirements are, first of all, that f of V1 plus V2 is equal to f of V1 plus f of V2, where V1 and V2 are any vectors in V. And the second condition is that f applied to C times V is equal to C applied to f of V for any constant or scalar C and any vector V in V. All right, so let's stare at these conditions for a moment. So the first thing to notice is that there's a slight subtlety here, which is that this addition right here is addition of two vectors in V. Right, V1 and V2 are vectors in V, and I'm adding them, and this is a vector in V. Whereas this addition in here is addition of two vectors in W. F is a map from V to W, so this is in W, and this vector is in W, and I've added them in W. And so it's saying that F takes addition in V to addition in W. It relates the addition operation in the two vector spaces. And similarly, this scalar multiplication here, if I write it as a dot, this is scalar multiplication in V, whereas this scalar multiplication here is scalar multiplication in W. And so again, F is relating the scalar multiplication operation in V to that in W. And so, I mean, what's a vector space? A vector space is a set with two operations on it, addition and scalar multiplication. And a linear transformation from one vector space to another is one which has this very simple behavior with respect to those operations. All right, well, let's just illustrate this with a bunch of examples. So, very important special case of this is when V and W are both the one-dimensional vector space, which is to say the real numbers, and this F is, you can think of this as being the usual y equals f of x, which you graph in the xy plane. This is a function in the most basic sense of the word. And an example of a linear function, a linear transformation, is f of x is equal to 3 times x. Another example is f of x is equal to 0. A third example is f of x is equal to minus x. Those are all linear functions, and the graphs of these three functions are f of x is equal to 3x, looks like something like this, and let's call these f1, f2, and f3. This is the graph of f1. The graph of f2 is just this line right here, and the graph of f3 is this line right here. And the graph of each of these functions is a line through the origin. It's a line, and it has to be through the origin. And in general, the most general linear function from R to R is f of x is equal to c times x. And so that's a line with arbitrary slope. I guess I'll call this f4. This is the line with any slope going through the origin. Well, let's see. Let's check the conditions y here. I'll just do the last one, which is the general one. If f of x is equal to c times x, the fact that this is linear, what do you have to check? Well, you have to check that f of x1 plus x2 is equal to f of x1 plus f of x2. Is that true? Well, what is f of x1 plus x2? This is c times x1 plus x2. And I want to know, what's f of x1? Well, that's c times x1. And what's f of x2? c times x2. Is that true? Of course, by the distributive law, yes. And similarly, I need to know that f of bx is equal to b times f of x. And I'm using b instead of c here because I used c for the function. So I have to use a different letter here. Is this true? Well, what is f of b times x? Well, f of x is c times x, so f of b times x is c times b times x. And I'd like you to tell me if that's equal to b times, what's f of x? C times x. Is that true? Of course, that's true. So that's the confirmation that these functions are linear. Let's do another example. What if I asked you about the function f of x is equal to 2 plus x? Well, what's the graph of 2 plus x looks like? Looks like a straight line like this. That's a straight line. So is that linear? Maybe. So why don't you pause the video now and check and answer whether this is a linear function or not. And when you've decided what the answer is, start up again and we'll discuss it. All right, well, let's see. Is this function linear? Is it true that f of x1 plus x2 is equal to f of x1 plus f of x2 for all x1 and x2? Well, let's see. What's f of x1 plus x2? This is 2 plus x1 plus x2. And I'd like you to tell me whether that's always equal to f of x1, which is 2 plus x1, plus f of x2, which is 2 plus x2. Sadly, that's not the case. All right, the 2's don't work out. Here you have a 2, and here you have a 2, which adds up to 4, but over here you only have a 2, so the answer is no. And that's why the only linear functionals I'll say it again here. The only linear functionals from f to r, from r to r, the linear ones are exactly the ones f of x is equal to some constant times x, which is to say a line of any slope, but it has to be through the origin. All right, let's just run over a couple of quick other examples. F of x is equal to x squared, or x cubed, or 1 plus x squared, or anything else, sine x. All of those are certainly not linear. Okay. All right, let's look at something besides r, just going to r. So what if I bumped it up one level, for example, and I asked you for a linear function from r2 to r. So this is going to be a function of two variables, f of x1, x2, because that's an element of r2, and this is supposed to be a real number. So I want you to tell me a function which takes two variables and spits out a real number. So an example would be f of x1 comma x2 is equal to, let's see, how about x1 times x2, or x1 plus x2, or x1 squared plus x2 squared, or 3x1 plus 4x2, or ax1 plus bx2, or ax1 plus bx2 plus cx1 x2. There's a bunch of possibilities. So what I'd like you to do is pause the video and answer the question about each of these, whether they're linear or not. And this a and b and c here are arbitrary real numbers. All right, pause the video and come back when you think you know the answer. Well, let's see. x1 times x2, no. Yes. No. Yes. Yes. No. And I'm not going to work this out in detail. I'll just say what's the problem. This multiplication messes this one up. This one's fine. Exponential, you're not allowed to have powers. These two are fine. This product right here messes this one up. And the other ones, notice that this one and this one are special cases of this one, where you take a is equal to b is equal to 1, and here you take a is equal to 3 and b is equal to 4. Fact, the general linear transformation from R2 to R1, to R2 to R, I should say, is you take f of x1, x2 is some constant times x1 plus some constant times x2 for a1, a2 arbitrary constants. And I'll leave it to you as an exercise to check. Check every such f is in fact linear. Check the linearity conditions. All right, so if there's questions about that, I can talk about it in class. Here's a generalization of this. I'll call this a proposition. Consider the functions from Rn to R. Then if f is linear, if and only if it's of the form f of x1 through xn is some a1 x1 plus dot 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 a n xn for some a1 through a n, some real numbers. So that's just the obvious generalization of this fact when n is equal to 2. And notice that if you fix a vector, I'll call it v, and make a vector out of these a's, a1 through an, that's I've just taken these coefficients and made a vector out of them, then f, f of the vector x is simply x dot v, right? Because that's what this is. All right, this is the dot product of the vector a1 through an with the vector x1 through xn. All right. Well, I'll write this another way. Another way to think of this is that f of the vector x, which maybe I'll write it out in coordinates, x1 through xn, is none other than the vector v, which is to say a1 through an times x1 through xn, written as a column vector. This is simply matrix multiplication, right? Because if you multiply this vector times this vector, you get this thing here. Well, here's really the big theorem from this chapter. Suppose I told you I had a function f from Rm to Rn. What are all the linear functions from Rm to Rn? Well, let's write a vector of Rm as x1 through xm. I want a function which takes an m vector and gives me an n vector, which I'll write as also an a column vector, y1 through yn. Well, generalizing the previous example, you'll notice that if I multiply this n vector by an n by m matrix, I can do that because m is equal to m, and what I get out is an n by 1 vector, which is to say this, and which is to say an n vector. So this is an n by m matrix. So I'll write this as a11 dot 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 down to a1m, a21 through a2m, down to AN1 through ANM. And the big theorem is that F is linear if and only if F is of this form. Which is to say, F is given by an N by M matrix. Okay, so that is a very important interpretation of what matrices mean, and I've sort of used this already. If you think about some of the stuff we've talked about earlier, you kind of know this. When you think about solving linear systems and kernels and all of that stuff, sort of behind the scenes is the fact that matrices are exactly the same things as linear transformation. Well, I think that's more or less a good place to stop for now. Let me make a couple of comments. So next time, I'm going to say basically the same thing holds, the same big theorem, where instead of this Rm, I'm just going to say you have a vector space V with a basis V1 through Vm, and instead of Rn, if I just put some other vector space W with a basis W1 through Wn. With those two changes, essentially the same thing holds. And anyway, I'll talk about that next time. But also, there's a little bit of terminology. The book talks about a linear function, which it considers as a map from some vector space to another, which I'm calling, for me, this is what I'm calling a linear transformation. And it reserves the word linear transformation for the case when V is equal to W. And I'm not going to distinguish between those two cases. I'm just going to call both of those things linear transformations. So I'm more or less going to ignore this word function. And I might occasionally use it by accident, but really there's only one object for me. It's a linear transformation. Okay, see you in class tomorrow.